The student T distribution. The T distribution is based on degrees of freedom. With test for means, you will always have n minus 1 degrees of freedom in a data set of n elements. So if you're dealing with a sample size of 30, where n is 30, your degrees of freedom is always going to be 1 less, 29. The T distribution is bell-shaped and symmetric. It looks a lot like our normal distribution, and the mean's going to be in the center. Different from the normal distribution, again, is the degrees of freedom. Critical values and the student T distribution. When finding the critical values using the T distribution, and we do this for confidence intervals, you may use either the inverse T function on your calculator, or if you don't have inverse T on your calculator, remember in calculator lessons on Course Compass, I gave you a program that you need to download on your computer calculator. We're going to do some examples with finding critical values, and in all of these we're going to assume that the sigma, the mean standard deviation, is unknown. So that's why we're going to be using the T distribution. If sigma were known, we'd use the normal distribution, and it would go back to the normal CDF or inverse norm to find critical values. And we're going to just assume, for the sake of time, that all necessary requirements have been met. So find the critical value for a 99% confidence interval where n is 15. So since, again, sigma is unknown, we know that we're going to be looking at a bell-shaped distribution that is the T distribution. So here's all the T-scores. And the confidence level is 0.99, so we're looking at the middle 99% of the data. So forgive my curve, it's not as pretty as it should be, but my stylus is messing with me. So we're going to have 1% of the data on the outside, so that means this tail, the right tail, will have 0.5% there, and this would be 0.5% in the left tail as well. And we're looking for the critical value, the T-score that sits right at that boundary. So remember, when we need the T-score, we need the area, the probability of data that's below that score all the way to the left. So not just the 99% in the middle, but also the 0.005. So to find the critical value, we will use inverse T, and then the area all the way to the left is our first input. Hey! This was the song that I would warm up to when I played basketball in high school. Just FYI. So this is the area to the left. But remember, the T distribution is different from the normal distribution in that it is based on degrees of freedom. So your second input is always going to be your degrees of freedom. Now your degrees of freedom in this case is going to be 14 because your n over here was 15. So I'm going to input into my calculator inverse T, 0.995, that's that area all the way to the left of the critical value, and there's 14 degrees of freedom. When I do that, I come out with a critical value of 2.977. So now to find the critical values for a 95% confidence level with n equals 37. So remember, you have to be told n so that you know the degrees of freedom, and the degrees of freedom would be 36. Again, this is because we're using the T distribution. So, oh my goodness, I'm sorry, but I'm going to draw a better normal curve. Here we go. Oh, that's a little better. It's not a normal curve either. I should have said a better T curve. So there's my T distribution. And if I want a 95% confidence interval, I know the middle percentage is 95%. And that means the area on this left tail is going to be 0.025, because 5% would be on the outside and half of that would be on the left, which would be 0.025. So if I'm looking to find this t-score right here, I need the area all the way to the left of it, and I know that that area is 0.975. When I add these two numbers together, 97.5%. So to find that t-score, the t is going to be the inverse t function. The area all the way to the left would be 0.975, and my degrees of freedom is 36. And when I do that, my critical value turns out to be 2.028. Last example is a 90% confidence interval where n is 300. So again, if n is 300, my degrees of freedom is going to be one less, which is 299. And my t curve will look like so. And I've got 90% of the data in the middle for 90% confidence interval, which means on the outside I'm going to have 10%. So I'd have 5% in the right tail and 5% over here in the left tail. So let's get that 5%. And again, my critical t value is going to be this boundary here. And so what's the area all the way down to the left? That area is 0.95. So my t-score is going to be inverse t, area to the left, 0.95, degrees of freedom, 299, and my answer is 1.65. Hopefully you are able to do these on your own now as well. So here's an example of a confidence interval problem. It says, in a simple random sample of 106 body temperatures, the mean was 98.2 degrees Fahrenheit with standard deviation 0.62 degrees Fahrenheit. Construct a 99% confidence interval estimate of the mean body temperature of healthy humans. So first off, identifying what we have going on in this problem. We're looking for a 99% confidence interval for the mean. And the information that we're given is our simple random sample had 106 elements in it. So n is 106. The mean that they're talking about up here, this mean, came from the simple random sample. So that mean is going to be x bar. And so x bar is 98.2 degrees Fahrenheit. And the standard deviation is also coming from the sample. So that's going to be S is 0.62 degrees Fahrenheit. So it's very important to identify here when we look at our requirements for a test for a mean. Our requirements are going to be that we have a simple random sample, and we can check that. Yay, we do have a simple random sample. And the next requirement for a confidence interval would be either the population normal, meaning the original population of body temperatures is normal. We weren't told that, so that one we didn't have in play. But n has to be bigger than 25, so we could have one of these two in play. The population wasn't normal, but n was 106, which is definitely bigger than 25. And then the last requirement is that the population size, so all the body temperatures in the world, has to be bigger than 10 times n, which our n was 106. So I think the population size of all body temperatures of healthy humans is bigger than 1,000, so we're good with the last requirement. And then, because sigma's unknown, we know the sample standard deviation, but we don't know the population standard deviation. So therefore, we're going to use the t-distribution when we find our critical values. So our 99% confidence interval for the mean is going to be, actually this up here has to be x bar, doesn't it? That's x bar. So our 99% confidence interval would start with our point estimate of x bar. We then would subtract some margin of error, and then the other side we'd add that margin of error, because we could be wrong either to the right or the left of the mean. And so we already can fill in some of this, right? We know what x bar is, 98.2. So 98.2. We don't know what our error is yet, but we can go get it, and that's what we'll do next. So 98.2 plus the margin of error. So now we have to take kind of a side journey and find out what this m is all about. And the formula for m is the t-score, since we're looking at the t-distribution, times, again, the standard error. So now, again, two more variables that we need to know. The standard error for the sampling distribution for the mean is going to be estimated by the central limit theorem by s over the square root of n. So that's going to be our original standard deviation, 0.62 degrees divided by the square root of 106, and that comes out to 0.0602. So that takes care of the standard error part of the formula, but now we still need to know this t-score. So to find the t-score, that's our critical value that we were doing earlier. So we know that we've got a bell-shaped curve. We've got 99% in the middle, and that means there's 0.005 on the left tail, and my t-value is right here on the border. So I'm going to find that t-value by using inverse t, all that area to the left of the t-value, and that'll be 0.995, and my degrees of freedom will be 105, 1 less than n. And that value is 2.623. So now we can plug into our margin of error formula. M is equal to 2.623 times 0.0602. And so the margin of error is 3 times 0.0602, which is 0.158. So now we have the start of our confidence interval, and we found what m is as well. So it's just a matter of plugging in. So 98.2 minus the 0.158 and 98.2 plus the 0.158. And so our confidence interval becomes 98.042. And again, remember, this is degrees Fahrenheit. This is human body temperatures. And 98.358 degrees Fahrenheit. And that is the 99% confidence interval estimate for the mean. So this is an estimate for mu. So here's the cool part about confidence intervals, besides all this number crunching. is now the common belief is that the human body temperature is 98.6 degrees Fahrenheit. So a question might be, would this confidence interval support the claim that human body temperatures have a mean of 98.6 degrees Fahrenheit? What would your answer be based upon the numbers in your confidence interval? I don't know about you, but my answer would be, this is pretty far-fetched. 98.6 is outside of this region, far outside of the region from 98.0 to 98.3. And so it looks like our confidence interval suggests that human body temperatures are actually lower on average than 98.6 degrees. So your answer would be no. It appears that the mean, I'm just going to write mu because I'm running out of space, that mu is less than 98.6. Similarly, if another person asked or claimed that the mean human body temperature is 98.2, which I believe is a claim now, your confidence interval would support this, because 98.2 is somewhere in between. Oh, that's a bad color to use, but there's my yellow. 98.2 is in this region of 98.0 and 98.3. So that claim you could not reject. You would have to agree with that person. So there's confidence intervals for means with sigma unknown in a nutshell. Enjoy and have a good evening.